Okay, we are recording, we are live, audio and video's up. Welcome back to Statics. First off, major typo on the top because we are not in lecture 14. We're in lecture, what is it, 26, I think it is? Yeah, lecture 26. I pulled an old template and I just must not have changed it or updated it. So sorry about that. But a couple quick announcements. So exams been graded. Everybody in here should have gotten their grade report that shows how they did and all the deductions that were made. Again, I think the class did very well. The average was very close to even what we did on exam. I actually think it was a tad higher. I posted a video on Teams about that. It's only I think maybe 10 minutes. Everybody should take a look at it. And with that, I want to go ahead and jump into our next topic. Now, I'll go ahead and preface this by saying that I had mentioned calling an audible, and I guess I'm officially doing so. Let me stop the share and show you something real quick. Give me 1 second. Okay, so this is the schedule for the semester. Okay, it's popping up now. I've got my display here on the other screen. Let me just sort of put statics in a larger picture. This class is really about two things. It's about forces and it's about moments. We had test 1, which was sort of on forces. Test 2 is on moments. So what's left? What's left are applications. And so what I mean by applications is there's really 3 sort of things that we kind of need to assess before the semester closes. And that is we need to cover some basic analysis of structures, nothing super in depth, because you will cover this in some of your later courses. If you're a civil engineer, you'll have a course just on structural analysis. I know the professor for that class. He's not the nicest guy in the world. Just kidding, that's me. As for got to throw in some jokes. As for you mechanical engineers, you're going to have more specific courses on various components in mechanical, like machine element design, kinematics of machines, and so you're going to have directed stuff within your field. So we just need to cover some very basic concepts and sort of move on. The second application is friction. We do need to have some discussion of how static friction affects rigid body systems. And then the third is centroids. Really doesn't matter what order we go in. We just kind of need to cover all 3. And I thought centroids would be a nice change of pace. So it's definitely much more relaxed from a vector standpoint and all that. I'll go ahead and tell you that today, and probably today is the only day where we will have straight up calculus show up in our topics, but it's pretty easy stuff. It's not anything that's terribly complicated. And with that, I do want to get into it. So I decided to go ahead and rearrange the schedule and do centroids now. And so we'll have about maybe 4 lectures on centroids, and then we'll get into either structural analysis or friction. I haven't decided which, but I do want to give friction its the respect it deserves. Let me close this. Let's get into our topic for today, which is the wonderful world of centroids. So let's talk a little bit about what the deal is with centroids and the motivation for studying them and why this matters. I think it's pretty obvious why studying forces matter or moments matter. You're engineers. You're going to be designing stuff where we're applying forces to them. You're going to be designing buildings and bridges and dams and cars and airplanes and machines and all sorts of different things where you're going to take a system and put force on it. And so I think that's pretty easy to understand, that you've got to be able to understand the distribution of those forces so that you can determine the size and the constitutive properties of those members so that your system's safe. That's easy. What about centroids? Why are we doing that? Well, let's look on the 2 images or the 2 shapes above the line through the middle of the slide, the circle and the square. Now, I think it's pretty easy to characterize those shapes. And so if I asked you, okay, let's take the circle. What properties of that circle would be relevant, not just to define the circle, but maybe might be relevant for the engineer? Well, okay, how can we characterize that circle? We can probably characterize it by its perimeter. We can characterize it by its radius, maybe its cross-sectional area, its position, on the XY plane. All of those are numerical quantities. They're values, scalar numbers that represent a region in space. Just like the square. I've got a square here, so what characterizes its cross section? And when I say cross section, sometimes you'll hear me use the term section properties, and section properties refers to if I have a member and I cut through it and I look at the shape, whether it's a circle or a square or an I-beam or whatever, I'm looking at that cross section. So if I use the term section properties, that's what I mean. If I were to look at the square, I could define similar properties. What's the area? What are the length of the sides? All of those are numerical quantities that characterize this region. Well, one of the most important numerical quantities that we find in engineering applications, and I'll explain why, is the center. So if I have a circle, I think it's pretty easy to determine where the center is. If I have a square or a rectangle, pretty easy to determine where the center is. But what about this shape here below? Like, what even is a center of a shape like that? Like, how would you define the center of a shape like that? That's not easy. That's an irregular shape, and we need to have a quantity that characterizes it. We don't even use the term center. We use the term centroid. It's a mathematical description of a particular point on that region that has certain properties, and we'll define what those mean here in a little bit. Now, that's sort of like the basic, geometry problem, and I'm sure some of you are like, okay, Dr. Mike, that's great. We've got a geometry problem here. Who cares? Well, here's why we care. Engineers don't always deal with what I'll call easy shapes. I mean, if let's take a civil engineering application. I've got this dam that's retaining water, for a town or a city or whatnot. If I look at that concrete dam, that is not an easy shape. I've got rectangles, I've got a parabola, I've got all sorts of define rigorously. Don't worry, it's not bad. When I say define rigorously, what I mean is like a mathematical formula for it. It's really not as bad as you. And what you'll find is when we really start digging into centroids next week, there's a fairly simple process, a very simple algorithm for determining the centroid of a shape. We're going to do the calculus part today, and then we're going to move on to maybe some more real-life application stuff next week. But the overall point I'm getting at is that engineers don't always deal with shapes simple. Like if you're a mechanical engineer, okay, that gray, almost like teardrop shape on the side, that is a very representative cross-section of a wing on an airplane. And understanding the forces and distribution on that wing, just like the forces and distribution on that dam, are integral to determining what the location of the centroid. To give you a statics sort of tie-in to that, if you have a bunch of forces on an object, like a dam or an airplane wing or whatever, if those forces all go through the centroid, then they do not cause any bending moment. But as soon as those forces go away from the centroid, they cause moments. Okay, so if I'm not able to locate the centroid, how do I know whether or not these forces cause moment or not? So there's a very real statics-based application to this problem. Understanding how to locate the centroid is critical to understanding the distribution of forces and moments. But I think we, like I have here on the slide, we might be getting ahead of ourselves. We haven't even talked about what a centroid is. Okay, so let me give you a really basic getting started aspect. And I'm actually going to stop my share here because I kind of want to walk you through this on the board. So let's go back to that sort of amorphous blob shape that I had on that one slide. So let's say I have a plate. Let's say that this is a plate that's made out of steel or aluminum or whatever. It doesn't really matter what the material is. But let's say we have a plate. I'm purposefully drawing this as a very irregular shape. Okay, so a very irregular shape. And let's throw a coordinate system on here. Let's say that that's the y-axis, and let's say that this is the x-axis. Okay, and what I'm going to do is I'm going to take a small little piece, like a small little piece of that plate, and I'm going to take a look at it. So let's take a look at this little piece of the plate. And so maybe if I blow that up a little bit. So that's that little piece of that plate. This is the shaded region that you see right here. Okay, and so what we'll do, so maybe I'll sort of, do something like that so you can see I've blown it up. Okay, so if I'm looking at this this section here, what are some properties about this little piece of plate? Well, first off, this piece of plate has a weight, which we're going to call delta W. All right, so just how the weight of that little piece, and then it also has a location. Okay, so the location might be, we're talking about the location of that little center right here. I'm using a rectangle because a rectangle, I know where the center of that is. And so its location might be at something like x1, y1. And I'll say that because I'm going to call this element number 1. This might be element number 1. This might be element number 2, element number 3, whatever. And so when I say x1, y1, I'm basically saying the coordinates of that center point right there. Okay, so that's just a single element in the plate. Now what I'm going to do is I'm going to look at this like it's a statics problem. Okay, so this, if we're talking about weights, we're talking about forces and ultimately talking about moments. So this is the x-axis, this is the y-axis, so the z-axis goes in and out of the screen. Okay, so if I were to sum forces, let's say if I sum forces in the z direction, well, let's take this to a statics problem. If I sum forces in the z direction, okay, then what's going on here? Well, if I sum the forces in the z direction, I'm going to have the weight of this little element plus the weight of maybe another one of these elements plus the weight of the third element. So in other words, what is the force in the z direction? It's hold on. What's the weight in the z direction? It's basically just the entire weight of the plate, right? And just add up all these little elements. But I also want to do a little bit more. You all know by now that there's not just equations of sum of forces. There's also sum of moments. And so if I'm summing moments, I propose we got two axes that we can sum moments about. We've got the x-axis and the y-axis. So let's sum moments about the x-axis. Okay. So I'm summing moments about this x-axis. So let's take a look at this element. Okay, so what's a moment? It's a force times a moment arm, right? So the force is going to be the weight times the moment arm. And here's the question. I want to ask everybody here in this class. Now, the coordinates to this point are x1, y1. Okay? How far is this element on the x-axis? In other words, what is that distance? And here's the question. Is it x1 or is it y1? It's y1. Exactly right. y1 plus, and then we're going to do the same thing for another element. y2 plus da-da-da-da-da. And then, so likewise, if I sum moments in the y direction, I'm going to have the weight of that element times x1 plus the weight of that element times x2, so on and so forth. See, if I bring it back to the slide here, again, I'm taking that little plate and I'm saying, okay, I've cut it up. Let's look at a single element, and I say, okay, this I characterize what's going on with that element, its force and its moment, and then I sum that up for a bunch of the elements until I've characterized the entire plate. Now, when I say here on the slide, I say notice the flipping of the subscripts. That's what I meant when I said like the distance from the x-axis are the y distances, and the distance from the y-axis are the x distances. That's not a typo. That's actually correct when you just think about it like you had here. How far is that element from the x-axis? It's whatever the y distance is, vice versa. Okay, everybody kind of with me so far on the general understanding on the concepts? Good deal. All right. So let's move on and let's see if we can start to come up with an idea that makes sense. Okay. So I propose we can define the total weight of the plate as the sum of all these delta W's, all these little elements. Okay. So and I'm just using summation notation. By the way, I'm curious, and if I don't want to just throw a bunch of summation notation if you've never seen this before. And please don't hesitate to answer yes. You're not going to hurt my feelings. Is there anybody here that's never seen summation notation before? I would think that you had when you took Calc 1. You should have seen that when you look at integrals. But is there anybody here that's never seen that before? The big Greek letter sigma. Okay. All right. So whoosh, summation. Don't worry, we're not going to like break out and do series or anything like that. We're not doing that in here. It's just to explain what's going on. We're not going to be breaking out any arithmetic series or geometric series or anything like that. Don't worry about that. I'm just using this as a means of expressing what's going on. So if I sum up all those little delta W elements, then the idea is that that's the total weight. Now, what if we wanted to idealize this plate as a single vector? And that's really, really critical for what we do with forces and moments, right? I mean, how do we define forces? Forces are just a vector with a magnitude and direction, right? And moments are that vector multiplied by its moment arm. Typically, in vector notation, we do that as r cross f. But if I've got a plate that's got this weird shape going on, I want to idealize that as a single W vector. The weight's pretty easy. The magnitude vector is pretty easy. I could just say it's W. The direction of that vector is actually pretty easy because the whole plate is applying load about the z-axis. So I've got a single vector that's got a magnitude of W that's pointing downwards in the z direction. That's fine. But where do I put it? Okay. Well, I propose that I put it wherever I generate equal moment about the x and y axes. So if I look here, and this is really the critical part right here, let's take the moment about the x-axis. I propose the moment about the x-axis can be written in the summation notation. Just sum up the delta W times those y distances, okay? And that's going to give me a moment about the x-axis. But the question is, can I take that quantity and instead represent it as the entire weight of the plate times some magical distance? We'll call it y bar, okay? Well, answer is yes. What do? I solve for y bar. If I take the sum of y times your deltas divided by the weight, which is the sum of your deltas, your sum of your delta W's, I get y bar. What are you doing here? You're basically computing a weighted average. Let's go back to just basic, math and basic statistics. How do you compute a weighted average, right? Well, you take a bunch of numbers, multiply them by their weights, sum them up, and then divide them by the sum of the weights. That's a weighted average, right? That's all we're doing here. Where is the center of gravity? It's the weighted average of all of your elements. That's it. You take each of your elements, multiply them by their distance from the y-axis, divide them by the sum of the weights, and that's the location of the center of gravity measured from the y-axis. Same thing for the x-axis. That's simple, okay? And so I'm calling that the center of gravity. And the reason I'm calling it the center of gravity is because what you see here is in reference to weight, okay? So is everybody with me on that concept? Again, if you can compute a weighted average, you can do this. It's really not that bad. Now, first off, before we delve into centroids, let's see if we can refine this estimate a bit. So I propose we've got the center of gravity, which is the sum of your, weights times their moment arms divided by the sum of the weights. But I'd like to refine that estimate. See, the problem with this definition here in the gray is this definition is contingent on these delta W's. In other words, the bigger I choose a delta W, I might not have as good of an estimate. The smaller those delta W's get, the better the estimate's going to be. It's going to be a lot more summation, but my answer as to where the X and Y coordinates of the center of gravity are is going to be better. And so let's go back to calculus. Remember how when you first start defining a definite integral, how do you do that? You take a little slice under a curve, you know, that little rectangle, and then you make those rectangles tinier and tinier and tinier, and you sum them up, and then all that sum, that summation, it turns into an integral, right? So in other words, if I integrate this region, that's the weight. If I take this this weighted average that you see right here, you know, the integral of x times dw and the integral of y times dw, this is just me writing all of this in integral notation. I'm just doing the same thing, just right in terms of integrals, okay? Does that make sense? Oh, hey. Now, I want to go back to this thing here on the board because I want to make a point on something. So I want to take a look at this little element. Let's take a look at this this little element. I want to talk about delta W. Okay. Now, how would I compute the weight of this element? How would I do that? Well, I propose that this element is going to have some thickness, right? So it's going to be the thickness times this shaded part right here, which I'll call the area, right? So if I take the area times the thickness, what I'm doing here is basically computing the volume, okay? And so, you know, think about this. If I have the volume of something, let's think about it like this. If I have the volume of something and I multiply it by its density, I get its mass, right? If I take the volume and I multiply it by its unit weight, in engineering, we always use a lowercase gamma to represent unit weight. So if I take the volume of something and multiply it by its unit weight, so unit weight is like, for instance, I'll give you an example. Like the unit weight of water is 62.4 pounds per cubic foot. So if I have a cubic foot of water, that's 62.4 pounds. So if I take the unit weight of a material, multiply it by its volume, that'll tell me its overall weight. Well, I'm going to, you know, go back to this this refined estimate. We've located the center of gravity. What about this term, the centroid? Well, here's what's going on with the centroid. If I look at each one of those elements can be computed by taking the unit weight times the thickness times the area. But here's the thing. If I go back to that plate example I was talking about, well, all the elements have the same plate. All of the elements have the same thickness. So really what was the key piece of information is not the center of gravity, but really the center of area. In other words, the center of that region, that closed, you know, shaded region. That's really what I'm interested in, because the center of So instead of representing this sum of x times the weights divided by the sum of the weights, instead I'm going to represent it as the sum of x times area divided by the sum of the area. And so whenever you, am I still here? Oh, I saw the thing in chat. You know, you say that. I'm looking here on my other computer and I see a little weird symbol that looks like I might have had a connectivity issue. So I apologize. If I cut out, let me know. Going back to this, you know, if we're talking about the center of gravity is a weighted average of the weights. But really what we're interested in when we're dealing with sections of uniform thickness and of constant material is the center of area. And we never really use the term center of area. We call it the centroid. And so what is the centroid? It's sort of a weighted average of the area. That's pretty much it. The Centroid has some very, very real applications in engineering, and I'll give you a real quick example of one. So, for instance, this is my little I-beam that I use a lot of times when I am in structures and concrete and steel design. Let me show you something. Okay, so this right here is the what I'm talking about, the cross section of the beam. So you've got your flange, and then the center portion here, we call that the web, like Spider-Man, like web. Now this particular shape, okay, so this is an eye shape. I might ask, what's the centroid of this shape? Well, I can go ahead and tell you the centroid of that shape is going to be about, I don't know, like right there, okay? And then I think that makes sense. Like it's just the middle of the shape. I mean, it's symmetric. It's that's pretty simple. Okay, why does locating the centroid matter in an engineering application? Well, if I have this I-beam, I'm pushing on the I, like I'm taking it and I'm pushing on it like it's a column in a building. If the load goes through the centroid, then I'm not bending it. I'm just pushing on it. But as soon as that load goes away from the centroid, so in other words, instead of loading it like directly on the centroid, I load it over here. As soon as I load it away from the centroid, I start to bend it. But I don't know how much bending there is if I don't know where the centroid is. So locating the centroid is very, very important. Again, go back to what I was saying earlier. This would be a section of uniform material. It's all the same rubber beam. And it's also sort of uniform thickness. I mean, if I just consider this section, it's not like the thickness changes, not like this has a thickness than this. And when I say thickness, I'm talking about, in and out of the screen. So yeah, there's very real applications in engineering to locating the centroid. Likewise, with the center of gravity, we can improve our estimate for the centroid by breaking out some calculus. Now, ultimately, what we're going to do, and we're going to start this next week, this is what I was meaning when I was saying it's going to get easier, is we're ultimately going to be concerned about doing this. We're going to take a region and try and break it up into simple shapes. In other words, we've got a closed region, this really weird shape right here. That really weird shape is just a collection of rectangles and triangles. And so if I know the centroid of some basic shapes, like some rectangles, some triangles, what have you, then I can use those to determine the centroid of some really funky shapes, if you will. But I want you to respect what those formulas are and where they come from. For instance, if you look at a triangle, and you're actually going to do this one for your homework assignment, you'll find that the centroid of a triangle is like a third of the way from the top. And I'm actually kind of telling you the answer to one of your homework problems. But I want you to go through that process of actually deriving it yourself. And in order to do that, I want to go through an example with you. And I don't want you to think of the calculus as being all that scary. Again, I'm not trying, this is, when I say calculus, we're not doing some integral of e to the x times the tangent of the square root of x. It's not complicated stuff. It's really, really basic integrals. I just want you to be able to use them towards a somewhat real life problem. I have here the graph of y equals x squared. Okay, and so if you look at the shape, if I look at, let's say, this point right here, what are the coordinates of that point right there? It's 3, 9, right? So that's the point 3, 9. And how did I get that? Just y equals x squared. So you can see how I've got the dimensions drawn out. I've got 3 on the bottom, 9 on the top. What I want to do is determine the centroid of this shape. In other words, there's a magic point, somewhere like right there, and I want to know the coordinates of that point. And from a physics perspective, if I were to take that shape and balance it on the head of a pin right there, it would not fall over. That's its balance point, and that's where if I put forces through that point, I generate no moment. I kind of want to walk you through how to do this. It's really not that hard, really, really basic. So let me stop my share and bring up my notebook. Okay, so here's the problem, and let me get my keyboard detached. get my power cord plugged up. I accidentally unplugged that. Yep. There we go. That's a little better. Okay. So what I want to do is I want to determine the location of the centroid. Now, in order to determine the location of the centroid, what I'm going to do is I'm going to determine an x bar and a y bar. Now, my basic equations are going to be the integral of x dA and the integral of dA. That's basically what I'm going to do. Integral of x dA, and then the same thing for the y bar. I'm just going to integral y dA over the integral dA. I keep drawing integral dA. So this is just a weighted average. You know, nothing really all that complicated. Let me move that down a bit. It's just a weighted average written in integral form. Okay. Now, this might be a new way of referencing, of writing an integral. For instance, you're probably used to something like f of x dx from a to b. Okay. That's probably what you're used to from a calculus perspective. I'm lazy. Okay. So I just write that as dA. Okay. And so what I'm basically doing is I'm taking these little dA elements and I'm adding them up across the region. That's basically all we've got going on. So let's first off see if we can determine the area of this region. Okay, and so the area would be defined as the integral of dA. In other words, if I sum up all those little dA elements, just like I'm summing up all those little delta A elements, that would give me area of the function. Now I'm going to sort of belabor this explanation. You could probably work this one out. So here's the x-axis, here's the y-axis, and so let's say the shape looks something. Let me break out some colors here. Let's say the shape looks something like that. Okay, and I want to determine the area under the curve where that's 3. So this is x equals 3. And this is x equals 0. And I want to determine all this area under the curve right here. That's what I want to determine. Okay. Well, in order to do that, let's go back to basic calculus. Okay, so I'm going to figure out what's going on with a little rectangle, like one of those little itty bitty rectangles. Okay, and there's a reason I'm looking at this rectangle format, and the reason why I'm looking at the rectangle format is because of how I have to rewrite some of these functions in a bit. Now, how wide is this rectangle? Let's talk about how wide. I propose that the width of that rectangle is a little dx, right? It's a little delta x, a little change in x, a little tiny width, that's dxy. Now, that's the width, okay? What about the height? Okay, how far is it from the x-axis to the top of the rectangle? This dimension is y. Okay, so if I'm looking at this dA term, I propose equals y dx. Or what is y? Y equals x squared. So x squared dx. So if I want to determine the area under the curve, I integrate, I sum up all my dA terms. What does that mean? I integrate x squared dx, and I go from x equals 0 to x equals 3. Now, that should be pretty easy, just setting up that integral. Everybody with me so far on this? Any questions on setting it up? I mean, that should be pretty simple from Calc 1. Now, let's evaluate. So help me out. What's the integral of x squared? I'm going to evaluate it from 0 to 3. What's the integral of x squared? I know y'all know that. There we go. 1/3 x cubed. So x cubed over 3. And then how do you evaluate a definite integral? You plug in the top number minus you plug in the bottom number. So we do, I'm going to factor out the 1/3 because I'm lazy. So 3/3 minus 0/3. So 3 to the third is 3 times 3 is 9 times 3 is 27. Minus 0 is 27. The area equals 9. Okay, before I move on, everybody okay with that? Hold on, I got a thing pop up over my chat here. Okay, now, in order to determine the location of the centroid, we need to do 2 more integrals, okay? The first that we need to do is not just the integral of dA, but we need to do the integral of x dA, okay? Because what I'll do is I'll take the integral of x dA divided by the integral of dA, and that'll tell me x bar, okay? Now, first off, for those of you, if you want a name for this integral, what we do is we call it QY. Q is a letter that we use for a first moment, and remember the indexes flip, right? So if it's the, how far, is it from the x-axis, some distance y? How far is it from the y-axis, some distance x? So this, if we wanted a name for this, for those of you that like the terminology, we call this the first moment about the y-axis. And for those of you that are curious, if we did the integral of, let's say, x squared dA, that would be the second moment about the y-axis. And we have a name for that in engineering. We call that the moment of inertia. And that is a very important quantity in mechanics. So third moments, fourth moments, honestly, they don't really matter all that much. But the first and second moment are very important. Okay, so now what we're going to do is we're going to integrate 0 to 3. We're going to have x squared dx. But then we're going to multiply it by x. So I can see the difference between the 2 integrals. The first was the integral of x squared. Now it's the integral of x to the third. What is the integral of x to the third? Making sure everybody's awake on this Friday. 1/4. 1/4 x to the 4th. So x to the 4th over 4. This is 1/4. Then we've got 3 to the 4th minus 0 to the 4th. And so here, I'm going to, let me do some stuff here. All right, so QY is 81 over 4. And so right off the bat, if we wanted to, we could say that QY over A is the integral of x dA over the integral of dA. That's going to be x bar. And so x bar is 81/4 over 9. And so 81/4 over 9, that's going to be 9/4. X bar is 2.25. Boom. Okay. Now, so if here's my region, let me go back to the very beginning. I'm trying to find, that magic point right here. I'm looking right there. If I'm trying to find that magic point, the coordinates of that point are 2.25 comma something. I don't know what that something is yet because I haven't determined y bar. But that, if I wanted to balance that shape on the head of a pen, put it at 2.25 comma something. Now, what about that something? How do we do that something? Okay, this is where things get maybe a bit challenging. So let's go back to the graph. Okay, let's go back to the graph. So here's the shape. I'm going to draw this kind of big here. Okay, so this is the x-axis. This is the y-axis. Here's the graph. Here's this. And we're trying to determine the properties of this shaded region. Now, let's recall what we had found last time. Remind me, what was the area of this shape? Help me out. 9. Okay. All right. That's important. Keep that in mind. All right. Area is 9. Now, the equation of this curve is y equals x squared. Okay. Now, I'm going to rewrite this another way. Okay. If y equals x squared, I propose that another way of writing it is to solve for x and write it like this. Okay. So, this is y equals x squared. The idea is, okay, y in terms of x, this is x in terms of y. Okay. So y equals a pile of junk as a function of x, x equals a pile of junk as a function of y. There is a reason I'm doing that, I promise you. In order to determine the location of the centroid about the y-axis, what we have to do is this. In this integral, we had a bunch of vertical rectangles and we summed them from left to right. Now what we're going to have to do is we're going to have to define a bunch of horizontal rectangles. We're going to have to sum them from top to bottom, or from bottom to top, right? So let's handle that. Okay, first off, I'm going to move this arrow here because really I'm just talking about the curve in general. I'm not talking about that particular rectangle. All right. Remember, this dimension was 3, and this dimension was 9. Come on. Oh, I didn't mean to do that. All right. So let's do the same thing we did here. Let's talk about the thickness. I propose that before, the thickness of that rectangle was what? Dx. See that up here? See the thickness is dx. I propose here the thickness of the rectangle is dy. All right. Now, that's the thickness. What about the width? Okay. Now, if you say that the width of this rectangle is x, that would be wrong. Okay. It's not x. And here's why. This dimension is x. I mean, what is x? X is defined from the origin to the curve. So this dimension is x. So if that dimension is x, what is this dimension? It is 3 minus x. Now, let's say you're like, hold on, Dr. Mike, I don't believe that. That doesn't work. I'll show you and can prove to you that it works. And here's why. Let's take a look at that little differential slice. Let's look at dA. Okay, dA, how do I define the area of that little slice? It is 3 minus x times dy. But what was 3 minus x? Well, what is x, I should say? It's the square root of y. So here's how you can check if what you have done is correct. Watch this. I propose if we were to recompute the area, and we don't have to recompute it, but if we integrated dA, I have a new way of doing it. Instead, we could integrate 3 minus the square root of y. Instead of evaluating from 0 to 3, we're doing this vertically. So we evaluate from 0 to 9. Okay? Now let's just test this and see if it works. If we test this, what do we get? We get, what is the integral of 3? Well, the integral of 3 is 3y. Now, let's go back. Now, this is some calculus here. So the integral of the square root of y. Remember, a square root is an exponent. So, this right here is just y to the 1/2. So how do I integrate y to the 1/2? I do y to the 3/2, divide it by 3/2, evaluate from 0 to 9. And what do we get here? So we get 3 times 9 minus, and if I flip that fraction, I get 2/3, 9 to the 3/2, minus, and if I plug in 0 for both of these terms, I'm going to get 0. And I promise you, if you chug that out, you're going to get 9. Why? Because the area is 9. I just did it a different way, okay? Now, why is this important? Here's why it's important. Because now we need to integrate y dA. And so we need to integrate that in terms of y. We'll call that qx. And so now I need to evaluate this integral, but I need a y in there. Okay. This might hike up the, we got to, roll up our sleeves and get our calculus muscles flexing on this. So I'll walk you through this integral. It's not too bad. So we integrate 0 to 9. We've got 3y minus, if we have y times y to the 1/2 power, that's y to the 3/2 power. And so if I integrate that, I'm going to get, what do I got? I got 3/2 y squared minus, and then this is going to be y to the 5/2 divided by 5/2 or multiplied by 2/5. Did I do that too fast, or are you all okay with that? Then we plug in the top number. Minus, plug in the bottom number, and those are all going to be 0. And so we get a qx. If you chug this out in your Casio, you will get, what is that? It ends up being like 243 over 10. So, if we go back to what we had before, x bar was qy over a, y bar is qx over a, which is 243 over 10 divided by 9, which is going to be, when you check that out, it's like 27 over 10. So y bar is 2.7. And the coordinates of your centroid are 2.25, 2.7. I'll move this down here. All right. I know we've got a couple minutes. What do you think? Any questions? So if you go back up here, the coordinates of that point are 2.25, 2.7. If I were to break out a 3D printer and print out that shape and stick that on a head of a pin at those coordinates, it would balance. Would you be willing to review where the 3x came from? Where the the 3 minus x. Okay, the idea is right here. So we're looking right there. The entire curve from the y-axis to the outer bounds is 3. Okay, but the point is that what if you measure right there, that distance is x. That distance is x. That distance is x. So if we're looking at that little rectangle that you see, the little shaded red, oh man. Okay, if you look at this little shaded red rectangle, the distance from the y-axis to the curve, that's x, but that's not the width of the rectangle. The width of the rectangle is 3 minus x. Okay, does that make sense? X is always from no. That's not silly at all. This is really important. Okay, this is the stuff that trips people up. The distance from the y-axis to the curve is x, just like the distance from x-axis to the curve is y. That's why that first integral is a lot easier. There's a little bit more going on with that second integral, and this is y. No pun intended. Any other questions before we call it? We'll delete these. Keep in mind, these notes are all in the Microsoft Teams channel. I do want to show you something super quick on your homework assignment. This is your homework assignment, and what I want you to do is I want you basically to repeat this for a triangle, particularly this triangle. And I left it as B and H because I want you to sort of look at this and say, okay, where is the centroid? Like, where is that point for a triangle? You could look it up, but I want you to go through the process of deriving it. And I gave you a couple hints, like what's the equation of the diagonal line? You know, equals mx plus b, find the slope, find the intercept. And during integration, this is a hint, treat the sides of your rectangles as constants. Makes it a lot easier. That's all I have, everybody. I know everybody's long enough. I know you got class. I will see you all next week. You all have a wonderful weekend. Stay safe, stay healthy. We will see you on Monday.